I will explain the road safety issues that we identified during our site observations. The first issue is alignment and sight distance. The road has a curved and slightly elevated approach, which reduces the available stopping sight distance for drivers approaching the hostel entrance. In addition, visual obstructions such as road signs and parked vehicles further limit the driver's field of vision, increasing the risk of collisions. The second issue is speed management. We observed that many vehicles travel above the recommended speed limit of 30 to 40 km per hour near the hostel area. Although speed humps are provided, some are faded or spaced too far apart, making them less effective in reducing vehicle speed. The third issue involves pedestrians and other vulnerable road users. Many pedestrians cross the road at uncontrolled mid-block location instead of using designated crossing. We also found that the zebra crossing markings have faded, and the lack of proper warning signs and lighting reduce visibility, especially at night. Lastly, access management and operation are another concern. Vehicles stopping or queuing at the hostel gate often block the through lane, creating turning conflicts and traffic delays. We also observe motorcycles waving through traffic and making informal U-turns near the entrance, which increase the potential for accidents. For this slide, I will present the literature review for our traffic engineering project. Traffic engineering is the branch of civil engineering that focuses on the planning, design operations, and management of road transportation systems. Its main objective is to ensure the safe and efficient movement of vehicles, pedestrians, and goods. Another important concept is the level of service, or LOS, which classifies traffic condition from level A, representing free flow traffic, to level F, representing heavily congested traffic. This classification helps engineers assess road performance and determine whether improvements are needed. Next, I will explain the technical standards that were used to assess the road conditions at our study locations. The evaluation was carried out based on the Arahan Teknik Jalan issued by the Public Works Department or JKR Malaysia, together with the Highway Capacity Manual and relevant road safety guidelines. For alignment and sight distance, the available stopping sight distance was compared with the minimum requirements supplied by JKR. The curved road alignment and visual obstructions reduce driver visibility, which may not satisfy the required stopping distance for safe operation.
My name is Nur Shafika Adina binti Zulkifli, and I will present about the procedure of our spot speed study. This slide will explain about the process starting from the preparation stage until the site selection. First, we prepare all the necessary equipment, include the data recording form, clipboard, pen, radar gun, and also safety vest. Before we start the study, we ensure that the radar gun was in a good working condition and review the operating instruction to ensure accuracy of the speed measurement. Next, we selected a suitable study location. The chosen site was a straight and level road selection located in front of College Melati. This type of road minimizes the influence of slope and curve on vehicle speed, allow us to obtain more reliable and representative traffic data. Finally, we record the general information of the study, include the location, the date which was 13 April 2026, and the observation time from 4 p.m. to 6 p.m. and the weather conditions which were good throughout the data collection period. This preparation step ensured that the spot speed study was conducted clearly, systematically, and accurately. Next, our team arrived at the study site about 30 minutes earlier to familiar ourselves with the area and set up the radar gun. The radar gun was positioned facing the upcoming traffic to ensure the accuracy of the speed readings. We also remain as inconspicuous as possible so that the driver will not change their driving behavior when they notice our presence. For vehicle sampling, we use a random selection method by recording the speed of every third and fifth vehicles. This approach helps us to obtain representative traffic data. Although the standard procedure recommends us collecting data for 1 hour or at least 100 vehicles observations are obtained, but our study successfully recorded 47 vehicle samples during the observation period. Throughout the data collection process, safety was our top priority. We maintained a safe distance from moving traffic, wore safety vests to remain visible, and avoid any action that might distract driver or interfere with normal traffic flow.
For this traffic volume study, a road with a two-way T-junction was selected as the study area. Traffic observations were carried out continuously for 1 hour. The number of vehicles was recorded at 15 minutes interval, which were at 15, 30, 45 and 60 minutes. After the observation period ended, all the collected data from the 6 traffic directions were combined and tabulated. The data were then analysed to determine the traffic volume, vehicle composition and traffic flow characteristic at the selected intersection. For result and data analysis, let's look at the process data table. Overall, we record data for a total sample size of 25 vehicles, where n equals 25. In this table, the speeds are grouped into class intervals of 5 km per hour. From this data, we calculate the middle speed and multiply it by the frequency to determine the overall distribution. Looking at the percentage frequency column, it is clear that the vast majority of the vehicles are heavily concentrated within a specific speed range. For a clearer visual representation, let's refer to figure 1, which is the frequency histogram graph. As you can see, there is one bar that stands out dramatically from the rest. The majority of the vehicles, specifically 16 cars, were traveling within the speed range of 20 to 24 km per hour. This indicates that the driving pattern in this area is highly uniform and concentrated around this range, while higher speeds above 35 km per hour show very low to zero frequency. Next, moving on to figure 2, which shows the frequency distribution graph. This graph plots the middle speed values along the x-axis. Once again, it reinforces the heavy concentration of speed with a sharp peak at the middle speed of 22 km per hour. The graph rises sharply from 70 km per hour and drops down immediately after 27 km per hour, showing that the speed distribution is not widely dispersed. Finally, let's look at the cumulative frequency curve to extract 3 key percentiles. First, P15 is 18.43 km per hour, which is typically used as a guideline to set minimum speed limits. Second, P50 is 22.07 km per hour, which is the median speed where exactly half the vehicles travel slower and the other half travel faster. Third, and most importantly, P85 is 24.12 km per hour. This 85th percentile speed is the standard engineering reference for setting the official post speed limit, as it reflects the safe and comfortable speed chosen by the majority of the drivers. Based on the traffic survey conducted for 1 hour, a total of 1,411 vehicles were recorded at the intersection. From the directional analysis, Direction 5 recorded the highest traffic volume with 752 vehicles, followed by Direction 6 with 583 vehicles. This indicates that most vehicles travel through these two directions during the observation period. According to Graph 1, the total number of vehicles increased throughout the observation period. The vehicle count was 318 vehicles at 15 minutes, 291 vehicles at 30 minutes, 375 vehicles at 45 minutes and reached the highest value of 427 vehicles at 60 minutes. So this is the graph 1 and graph 2, which is total vehicle versus time and percentage of vehicles.
In these slides, we will discuss the proposed safety improvement in the campus area. The main improvement is speed control, which is important to reduce the risk of accidents caused by fast-moving vehicles. In addition, road marking visibility should be improved to ensure drivers can clearly see lanes, crossing, and road direction. We also recommend enhancing pedestrian facilities such as proper walkways, safety signs, and guardrails in high-risk areas. These improvements are essential to ensure the safety of both pedestrians and drivers within the campus environment. In conclusion, based on the findings, vehicle speeds within the campus area are relatively high for a university environment, which raise safety concerns. The 85 percentile speed of around 60 km per hour indicates a potential risk, especially near curve and pedestrian zones, where accidents are more likely to occur. Therefore, traffic calming measures, improved pedestrian infrastructure, and stricter speed management are necessary to enhance overall campus safety. That's all from us. Thank you.